Hello and welcome to this presentation on the cross-modal associations of musical harmony, speed, randomness, and surface roughness. My name is George Athanasopoulos, and I will be with you for the next 15 minutes or so. Now, this presentation will be formulated as follows. First, I will talk a little bit about the theoretical background on the cross-modal associations between music and other domains. Then I will talk about the series of experiments that I have been doing with my colleagues from the Aristotle University of Thessaloniki. And then we are going to reach some conclusions. So first of all, and to begin with, the cross-modal associations between music and other domains is nothing new. There is a plethora of research out there dealing with specific music elements, mostly pitch and its modulation, as well as timbre, and its association to either linguistic metaphors or visual metaphors. Key work has been done in this area by a number of authors who have also looked at the topic in a cross-cultural manner. And what we usually see in the cross-cultural research of the association of music and other domains is that there are variations there. Also, I have done some work on the topic, but I will try not to bore you too much with it. Namely, there are specific and what we see consistent associations between the visual domain and music, especially when it is about its pitch. Now, if we, however, broaden the horizon and look at the cross-modal associations between harmonic dissonance and other domains, then we see that this is an issue at the forefront of interest in cross-domain studies in the last 10 years, mostly. So building upon the existing association between harmonic dissonance and surface roughness that we have seen in the past 10 years, here with this research, we investigate and further test how cross-modal correspondences in the harmonic aspect of music relate to analogy and metaphor in broader domains. Now, from our past work with my colleagues from the Aristotle University, and also from the work by you in 2018 and 2017, we see that there is a correspondence between auditory roughness and harmonic dissonance, together with visual shapes varying in roughness. Also, there are associations between hue and tactile roughness, as presented by Ludwig and Simner, as well as Slobodeniuk in 2015. Now, on the other hand, we need to talk about how consonance, dissonance, and roughness are perceived, because this is a massive topic. So what we see here is that the participant background in the perception of roughness and harmonic dissonance is an issue. Why? Because the majority of research has been done using Western participants, and lately, only lately, has it been done in a cross-cultural manner. And there we see that there are differences, and culture does affect the way that we perceive dissonance and roughness. Also, we see that a major influence is how the musical stimuli are presented to the participants, as well as whether they belong to a particular style and whether this style is known to the listeners. Now, in a past experiment that I have done with my colleagues, we saw and assessed the role of roughness in the association between consonance and dissonance and visual shapes. The visual stimuli that we had used in the past were 3D digitized images portraying surface textures, which varied in smoothness or roughness, also that is surface roughness. And regarding the auditory stimuli, we had a fixed melody which was reharmonized in many different styles. The reharmonization of the melody was done using the Chameleon software program, which is a fantastic program, and if you have the time to explore it, by all means do. The task that we asked our participants was essentially to match the auditory stimuli that they would listen to with the images as they were presented in front of them in the form of Likert scales. The results that we got from that first experiment that we presented last year was there was a high correlation between dissonance and visual roughness, which in turn has probed us to continue our investigation in the cross-modal aspect of acoustic features involved in harmonic dissonance perception. Now, let's have a look at the current experiment and what we have been keeping ourselves busy in the last year. So for this current study, our aim was to assess the relationship, if any exists, between harmonic dissonance expressed as an average mean in musical stimuli consisting of chord progressions and two domains. First, visual roughness, as it is represented by Perlin noise images. I'll show you examples later on about what I mean. And also with a random motion speed of Brownian gas particles when the temperature increases. Again, I've got some nice visual props later on for you. So we wanted to assess whether an increased energy or tension, or how you want to call it, as represented by harmonic dissonance, could be tentatively associated with an increase in the speed of the Brownian motion particles and the corresponding increase in perceptible randomness. Why do we want to look into this? Because harmonic dissonance as a multisensory perceptual property makes full sense in having a go at if we want to justify why this might be a factor to explain consistent cross-modal associations between certain auditory and visual stimuli. So let's now have a look first at our participants. If you remember, I did say that the participant background does have a role here. So first and foremost, our participants were Westerners, and we separated them based on whether they were musicians or non-musicians based on the Olin test. The task that we gave our participants was to match auditory stimuli to the images that we would present to them. And also we asked them to evaluate consonants into their own beliefs, as well as the familiarity of the stimulus. So let's have a look now first at our auditory stimuli. We put together 6 stimuli, which ranged from fully tonal harmonic chords all the way to 12-tone chord series, which were rather dissonant in nature. We used a piano plugin from Finale to do the audio rendering, and we ensured that timbre, dynamics, and tempo remained constant throughout our stimuli. And let me just play for you a few samples. So here is a tonal stimulus that we put together. Whoops, let's try this again. Now here is an example of a tonal stimulus with a slight modulation. Here is a quasi-tonal stimulus. So now you get the idea. The more that we progress, the more dissonant, harmonically dissonant our stimuli become, all the way to something extremely dissonant. Now, regarding the sequencing of the chords, that is a completely different paper. So if you're interested in that, I highly suggest that you stay tuned for Mr. Yanis's presentation later on today. Now, let's have a look at our visual stimuli. So right over here, you see the Perlin noise images that we created using the Perlin noise maker by Mackay. So right over here, you see exactly what I mean. On the left side, you see images which are completely smooth, all the way to the right side, where you've got images which are rather rough in nature. Always we're talking about surface roughness here. We managed to achieve this gradient by increasing the pixel size. The second images that we used were what you see right here. So software, we were able to show randomization and increase in speed by tuning the temperature of gas particles from rather slow speed all the way to fully randomized motion and high speed into the gas particles. So let's now have a look at our results. So first and foremost, we saw that our participant background did not have such a large effect on the way that they perceive the stimuli. So we see that both musicians and non-musicians more or less responded in similar manner. So right over here, you see the results between the association between the stimuli and the images of Berlin noise. These are the surface roughness pictures, yeah? So now you see that there is an extremely high correlation between harmonic dissonance and rough images. This is also notable when it comes to the association of our stimuli with the speed of particles in Brownian motion. Here we see a slight differentiation between the musicians and the non-musicians, in that musicians perceived that the dissonance stimuli had an increased speed when it came to the Brownian motion particles, but more or less you see the same trend emerging right over here. In this chart over here, you see all the stimuli presented together with their respective mappings. And you also see that regardless if it was self-perceived consonants or consonants measured by Harrison and Peirce's model, we see that the participants responded more or less in the same manner. Let's have a look at the following diagram over here, which shows the correlation relationships between all aspects that we had a look into. So here you see that the mean reported consonants has a very high correlation with the consonants as it is measured by Harrison and Peirce's model, all the way to 0.901. At the same time, you see some spectacular correlations between Perlin noise and the stimuli, as in terms of their harmonic consonants, and also between the brown particles and the sound stimuli as well. Now, let's have a look at the conclusions that we can reach. So we can see here, based on our experiment, that consonance and dissonance can be mapped onto surface roughness and motion randomization and speed. These findings are in line with other cross-modal associations involving harmonic consonance and dissonance, and in a way we try to extend the growing literature on cross-modal association, which involves auditory stimuli. There is some very nice work done here in the past 10 years, and we're very happy to contribute to this body of work. Let's have a look at the broader conclusions that we can reach with our experiments. So, the ideal approach in order to understand the results of our research is to assume that there is a unity of the senses so as to represent the case of harmonic dissonance as a roughness, as opposed to harmonic consonance relating to smoothness. Now, we are continuing to collect insights into the multisensory processing of sounds, and the latest experiments that we have been running include tactile stimuli as well as cultural denominators. Last but not least, of course, we have to acknowledge the role of background culture. Now, we are aware and we fully agree that biological constraints as well as acoustic features of sounds determine the way that consonance and dissonance are discriminated and processed by the sensory system, and that is common across the board. However, culture provides the formalization of consonance and dissonance into music theory and harmony, and ultimately influences the aesthetic judgment and or even the subjective preference for consonance or dissonance. This is all from me. Thank you very, very much for your attention. I hope you all have a pleasant conference, and if time permits, I would like to hear any questions that you might have. Thank you very much.